Today's focus will be on our software, our GTS NX, and we'll talk about soil structure interaction, the different methods that we can do for doing this kind of analysis with Midas. I'll give a brief introduction to the company. Then I'll talk about some concepts for soil structure interaction. We'll cover briefly how to do with the substructure method with some of our other structural programs. Then we'll talk about mostly direct method, where we do both the structure and the soil in a single model. We'll be importing from our structural software a building, Midas Gen, to GTS and do the soil around it. And then we'll do the same for a bridge using our program Midas Civil to GTS, and then we'll have a brief conclusion. So let's start with the intro to the company, Midas. Midas is a worldwide software solution provider for civil engineering problems. We have everything from buildings to bridges and to geotech. Our headquarters is in South Korea, but we do have branch offices all over the world. What would be India or Russia, England. Here we're transmitting live from our New York office, where we handle basically this whole hemisphere. We have six main products for what is our the focus of today. So we have our structural engineering software, which is Midas Gen. We also have we have our structural engineering software, Midas Gen, in which I'll show how to do the soil structure interaction analysis with the substructure method. We also will show briefly our SoilWorks, which is a 2D only platform for geotech. It goes a little more or a little simpler analysis than just finite elements. It can do something else, like we will show today, like for Raft Foundations, we can do PY analysis. And then we'll conclude with the interaction between exporting a file from our structural software to our geotech software, and then our bridge software to our geotech software. So first, let's have a little background on soil structure interaction. This is basically the phenomenon of how we study the response of a soil in a building to an earthquake, how they interact with each other. Neither of these reactions are independent of each other. Now, we have two principal methods to do this. One is known as the substructure method, in which basically it's based on the superposition of events. We separate the problem. First, we do what would be known as a free field analysis on the site only on the ground, and we run basically a maybe time history analysis, a seismic wave, and we see or we study the displacements, the velocities, and the accelerations at the site of interest for where the structure might be. And then we go back, we calculate the rigidness that we simulated as a spring to then be placed on the structure itself. So basically we simplify the ground and say that we're going to say that it's behaving like some sort of spring, and there's different stiffnesses along the springs that can be used to simulate this ground. The other method is the direct method, in which we basically model the ground and the structure together in a single step, and we basically solve them simultaneously. And for this, you usually need a very powerful tool, like finite elements or finite discrete method. So with a direct method, as I was mentioning, you model the structure and the soil together. You basically are going to capture the behavior of the ground through constitutive models. These are numerical analysis theories. There's, for most of you who do geotech with some sort of software, you understand there's different constitutive models for different kind of behavior you're trying to capture. There's some for rocks, like the generalized oak brown, but then there's some for maybe like some clay, like the soft soil creep or camp clay constitutive models. So there's a whole theory behind all these different behaviors that you can model or capture for a 3D element using these constitutive models, and Midas has a long list of these, Midas GTS NX. So the benefit of this is that you can get a direct solution of your problem. It's a fully coupled analysis, and it takes away a lot of these simplifications that you do with the other method. You can even take into account maybe like the stiffness or the mass of the structure. However, as we mentioned, it's a more complex and time-consuming method relative to what would be the approach of just applying some soil springs to your piles and running it for the structural point of view. So let's just jump a little bit more into the substructure method. The typical process would be one, thus maybe some boreholes at the site to get information about the strata of the site of interest. In this case, we see that there was 3 boreholes at the site. Let's assume there's a structure that's going to be placed in the middle. And so we get this information about how the soil is distributed underneath. And we can already see here in the middle there's a pocket of some different kind of soil. We're not entirely sure of the property, let's assume here, or how it's going to affect the the structure. So for this, we then run a free field analysis without any structure in place, just the ground. We run, let's say, a seismic wave, and we get results of the accelerations. And we can see here the red represents the middle area. We can see here that this actually does amplify, it does increase the acceleration period, the peak acceleration period. And so for this case, it's kind of easy to visualize how the type of soil underneath is going to affect this acceleration. So then this can be used to calculate the stiffness, the impedance that can be applied to springs directly to the structure, and then we run a time history analysis with the structure using these springs. Let me briefly show you. Midas GTS NX can actually run free field analysis as well as 2D equivalent analysis. We see here I have some results for a very simple condition, ground condition, and I'm looking just basically at the different times of the accelerations as I'm going down on my tab. Midas GTS NX does have also 1D free field analysis. However, we also have other special conditions like we see here in 2D. We can apply transmitting boundary conditions. Let me go to our preprocessor so I can open some of these tabs and show you what it can do. In addition, we've also recently added free field boundary conditions. So here I'm going to show you what the transmitting boundary conditions are. And we can see here that we can apply them to the sides of the model. In this case, they've already been applied. We can also include it for them to be base, for the base to be viscous boundary or just free damper. And here I'll show you as well that we have what is now the free field boundary conditions that we can apply either to a 2D model as a line or a 3D model as a plane. So Midas GTS NX allows you to handle this aspect of the analysis. So as I was mentioning, you can, from this information, I mean there's different methods, but you can get your stiffness that you can apply as spring stiffness. So within the substructure method, we can see here that these springs that simulate the soil are applied to nodes on, it can be on the pile or it can be on the raft, but there's different directions to them and there's different properties. What is obtained from a PY curve, what is known as a PY curve that compares the ground reaction to the horizontal displacement. You get the slope of that, and that's basically your K, your spring stiffness. And we can imagine that if we have a pile that goes through several layers, that we will be using different PY curves for each soil composition that will be applied then to the spring itself. So for this, we actually have a 2D software that does this kind of PY analysis called SoilWorks. I will show you that briefly. In this case, we see that I've modeled a very simple raft with piles. We can see here there's the distribution from the vertical view, and here's the side view. We see we go through different layers. So I'll just take you through steps very quickly. The very first is just to define the material properties of the ground. We see here we have 4 different ground layers. We basically only input some parameters about the type of soil and some other properties that will be used during the PY analysis, like the modulus of subgrid reaction and such. Then we define some properties, structural properties about the piles themselves that are going to be used. In this case, we see that we're using some solid round piles. We can also talk about the diameters and maybe the properties, the material properties that we're using, concrete in this case, and then some modulus plasticity of this. And then we easily, since we're doing a 2D analysis, it's very easy in this case. We only have to worry about this, talking about the strata in the Z direction. So we can just give the material property by depth, by size of depth. So we're seeing here the distribution of this in the vertical direction of the different ground layers. And then lastly, we would just kind of give information about the foundation type itself. In this case, we compare two kinds of pile distributions, where we have a 3x3 distribution arrangement, and here we can control the type of connection for the tip and for the head. And here we give some values about the size of the raft itself. And here we have a 3x5, and we also give distance of the pile length itself. And after that, we would just, if you wanted to apply some other conditions, like the foundation load or water level and such, then we just run the analysis. In this case, I've already run it, so I'm just going to show you some results. When you run the analysis, you get these kind of results for each pile. So here we see that we have one activated. In this case, it's the corner one, and we see we get the horizontal displacement, the moment, the shear force, but we also get the reaction. So between these two, we can get the curve that we're interested in. So for instance, if I select the very middle pile, the center of everything, I can go here to a different tab, and we see here that I have what is showing as PY curves, and I can select one of these, and it'll give me these values, these PY curves that I can then just use to input these K as a spring in what would be the structural software that I'll be showing next. So it's just an example of how we can do directly with Midas SoilWorks a PY analysis. Just a little review of what we were showing. Once you've applied these springs, you can then do the dynamic part of the soil structure interaction analysis, which is to run a time history analysis in in Midas Gen, the structural software that I'll be showing. You can apply either a global, acceleration that's assumed to come from the bedrock, or we can even individually apply to each spring a different acceleration if that's what we want to vary the time and all that. So there's a lot of liberty in this respect from the structural point of view, applying these accelerations directly or functions directly to the springs. So let me show you how we do this with Midas. I'm going to open a structure like this that has some piles, and I'm going to show you how we apply these pile spring supports, and then do the same for a raft and how we do the surface spring supports. As I'll be showing you in Midas Gen, there's very few parameters that we have to basically input. Just you have to know the size of your pile diameter. You can select different types of soils, and all that's doing is allowing the software to choose different PY curves that has, like, internally based on the type of software you select, the type of soil you select to be used. And then you just have to input something else like the coefficient of subgrade reaction. So let me just show you that directly. We have here what would be different models. Oh, sorry, this is already run. Okay. Here we have a structure. We can see we have some different wall elements. We have some piles. In this case, we can run it without doing the soil structure interaction. We could just maybe fix the boundary at the tips of the columns without the piles in place. But since we added the piles, we can add a boundary condition that simulates the soil through these soil springs, as I was mentioning. So all we would have to do is go here to boundary. We have here what's shown as pile spring supports. And then we see here that very easily, like I was mentioning, I know the diameter of my piles is 2 feet. I choose a soil type that will choose a different PY curve depending on what I choose. And then I just input some value for the modulus of subgrade reaction, and then I just apply them directly to my piles. So for that, I can isolate my piles. I have different sections here in the table, and I could just tell it to only activate those. I can then just select everything that's shown and apply these soil springs, and we see here now that they've visually been confirmed and activated. So then I can just reactivate everything and run the analysis. I mean, depending on some other steps of adding maybe a response spectrum or a time history. Let's just say I ran the analysis as a time history analysis, and I then just get these results in this other model, the same model. I'm just doing it for saving time in this case. And we can see here everything from deformations to stresses to forces. I can, isolate it by the whole structure, or again, I can only activate what would be the piles in this case, if that's what I was interested in. Again, I could just go here to my tree menu and activate by section, even just for results. and I can see deformations. I could see all kinds of results that would be of interest for the foundation in this case, or displacements, or interaction stresses, all that. But again, this is from the structural point of view. We're using a structural software. This is for buildings, and we're simulating again this boundary condition, the soil springs. So back to the presentation. I just showed you how we apply these springs to the nodes on the structure and how we get these results, displacements, moments, curves, forces, all that. Let's do something similar now for a raft foundation. In this case, we're doing an example of the lease tower. These are, I think, some condominiums in South Korea. Must be like 50 stories high or something. So similarly, we're going to apply now distributed surface springs over the raft, and then we can see results like max shear or displacement. So let's open some of these models. Here we have the structure itself. We can see all the columns and beams, and it's been kind of given some random colors to make it easier to see. In this case, I can just again go to boundary, and now I'm going to use the surface spring supports. It's a little different approach. We can see here, depending on the type, if I do point spring, I can directly apply these K values that we were talking about from the SolWorks in the directions Kx, Ky, Kc. We can also do dampers, or I can just do elastic link. It's a different method. And here I directly just apply a modulus of subgrid reaction. Let's just do this. I'm going to activate my structure now by floor. I could do it by section, I could do it by material, I can do it by stories. So I can just say here, activate only the first story. It's a little easier for me to handle. I can do the side view, and then here I can just select, create a box around the nodes. We see here that the nodes of the raft have been activated, and I can just apply them directly if I want them to be tension only or compression only. And then I could just run this analysis again. And here we have a time history analysis, and we're showing the results for the whole structure. But again, if I'm only interested in what's happening in the raft, for this case, I can again just activate the very first floor, and now we're seeing here, some results for what would be, in this case, vertical displacements. And let me activate the legend so you can kind of see some idea. So we're seeing a few centimeters displacements in some cases, some very extreme points. And so for this example, we added just a random value for the spring supports, but ideally you would have that actual information from your geotech engineers that would give you a better result. But again, this is from the structural point of view. You're using springs to simulate the ground. What you ideally want to do is be able to model the ground with your structure for these kind of projects that we're talking about, a very heavy structure. So for those cases, Midas has the unique capability that allows you to export your whole structure to GTS NX, and then from there create the ground around it and use the direct method to run all sorts of analysis. You probably want to do maybe some consolidation analysis depending on your ground condition. We can do liquefaction analysis, or just a seismic analysis with your structure. So let's do that. Let's show you the steps for that. So in this case, we could easily just say here that I want to export this file for a format that's compatible with GTS, MXT. This is a Midas unique format. It will export the whole structure. So let's just say here, go ahead and save it. And while that's saving, we see here it's a very simple, even text format, actually, that just gives the information about the nodes and the properties and the loads that have been applied. And then I can just go to my geotech software. This is our Midas GTS NX. If you've been to some of our other sessions, you've seen this interface before. So here I would literally do the same. Instead of going to export, I would just go to import and look for the same format, MXT. And here we have the MXT format file of this tower that we've just imported or exported from the other program. And it'll take a few seconds to load as I'm also importing like all the properties of all the sections and all the loads that were with it. But we'll see the benefit once it's here. Give me a second. I'm going to just quit this. Okay. So this structure, once imported, it's considered to be already meshed. It already has, what that means is that it's not just the geometry, the structure itself has material properties assigned to it. And so we see it here. We even see some red arrows, and it's basically yellow. These are the loads that were imported. I can deactivate these just for the visual aspect of it. And then if I go to my other tab, my model tab, I can see here that materials have been imported. 17 materials in this case were imported, all related to the structure itself, as well as properties. I have here over 300 properties that are one-dimensional. All that means is these are all beams. So this structure itself used all different sizes of beams. If I go to my mesh tab, I can see here there's materials and there's property. I can see a little more detail how these materials are going to behave. If I go to modify, I can open them and see, some of their properties. Now, what I need to do is also, because I'm meshing the ground, I need to create some material properties for the ground itself. So here, what I need to do is import, there's different ways to do it. You could create it directly from scratch. Go to here, and you would select here a constitutive model. As I had mentioned before, there's different theories behind these constitutive models. So if we're doing something on rock, we might use generalized Oak Brown, and there's some different parameters you input. Or if we're doing something like on a clay, or maybe just more column is a very common, very popular, used for a lot of things. You input these other values on the behavior of the ground, nonlinear. We also have linear, like elastic. And here we could activate, if we wanted to do concrete, we could just tell it this will be used for a structural purpose. In the effort to save time, let's just import. We can also import from an Excel table these materials. And we see here that now I've created some materials for my piles, some soil that I'll be using, more column, and some interface. We can do pile interfaces. So now that I have the material, I basically just have to create some properties for it so I can tell the software this material will be used in a 2D or in a 3D situation. We see here from the structure we've imported some 1D beams, some 2D shells for the for some of the walls maybe. What I need to do is create first a 2D for the soil, as I'll be showing you later when I use it. Here I select the material, and I just tell it this is the 2D soil. I apply it, and then I'm going to do the same for 3D. So basically at the moment of mesh, I'm just letting the program know I need a material property that will be used in 3 dimensions using these materials. There's nothing really to it, and some special ones, maybe like interfaces, you can add a few more parameters. But here we'll see now I've created the 2 and the 3D soil. So now I can move on and go on to the part where I actually start to model the ground around my structure. What I will do for that is I'm going to first move my work plane. What we see here is a grid that's in an axis. In this case, it's in the ZX plane. This plane allows me to draw anything on it, and so it's very easy for when I'm doing geometry to use as a foundation, as a base to keep track of my drawings. So I'm going to go here to my geometry tab. We see here there's the work tree, and there's all sorts of information about the materials and the properties. Then I can expand on. I'm going to expand my work plane, and I can actually move it by just double-clicking. I can move the direction of the plane. In this case, I want the XY plane so that I can work on the ground. I'm going to change my view to top view. And then what I'm going to do now is I'm going to zoom out a little bit because I want to draw some squares of where the ground is going to go sufficiently far. So now I'm going to go to my geometry tab to my drawings. Here we see we have most CAD commands that you've seen in other programs, your Boolean operations, your extrude, your rotate, all that. Well, in this case, we're going to actually draw a rectangle. And I'm going to first draw a rectangle on the border of the raft that I've imported. And then I'm going to draw a second rectangle to simulate the border of the ground, the outer border of the ground. So now we see we have two drawings. The next step I want to do is I want the meshes to match. So I'm going to predefine some conditions on this border to match. I should know when I imported the structure more or less what size of mesh I use for the raft. So I can do that same size as a control on that border so that it connects with the rest of the mesh. So here I go to size control. I'm just going to select these four borders. Sorry. I'm going to give it a size of 3 because that's what I knew when I meshed my raft. And we see here if I use the preview command, it allows me to see where these nodes will be, and they line up, with the nodes of the raft itself, which is what I want. And so then I can now confidently mesh this layer and it'll connect properly with the raft itself. So here I'll go to Mesh 2D. We saw here that I've created a special 2D property for the soil. We see that there's all these other properties that came in with the structure. Those would be more of like concrete. So here I just tell it I want to mesh these four borders, and I want it to consider these lines as well. And I'm going to give it a bigger size just to keep this from being really heavy. So again, if I go to preview, now it shows me where these nodes will line up on the outer border. And I can just go to OK. And we see now here, if I deactivate the size control that I had just shown and inspect it, as I get close, I can see that the nodes from the ground line up perfectly with the nodes of the raft. So now I can actually extrude a mesh. In Midas, you can extrude not just geometries, but you can also extrude meshes. And I'm going to create a 3D mesh out of this 2D mesh. So what I want to do is select the meshes carefully, as close as I can to this flat. We see here that I've activated or selected the nodes in turned green. I want to give it a direction. I can select directly from my view here the z-axis. I'm going to give it a distance, -100, since I want it to go down. And I can give it some divisions here, let's say 5 divisions. And I assign the material property for it, so this would be just our 3D soil. And if I go to preview, I can see how this mesh will be created before I've accepted it, and then I would have to undo it. So this looks good to me, so I'm just going to go to OK. So now, depending on the kind of, I'm going to deactivate the work plane. Depending on the kind of analysis we want to do, we could potentially, just do some other modifications, add some piles. We could, do a consolidation analysis defining some other properties, or we can just do a linear static. Let's just do it for time's sake. I'll show in the next example with the bridge how to do a nonlinear time history. So if I wanted to do just a linear static and maybe compare adding piles and not having piles in the structure and how it's going to settle, I can just add some constraints. I could directly tell it the program by selecting nodes, fix displacements in certain direction, fix rotation in certain direction, or I can just tell the program to do it automatically, and it's smart enough to know, depending on which side of the face, it will add the constraints properly. So we see here we have like the bottom boundary has 3 little arrows. It's fixing displacement in TYC. But then other faces, it's only in one direction. It's depending on the plane. So here I have everything I need now for a very simple analysis. I could just go now here to analysis. I have the loads created that I imported from the structure. So I could just go right-click here and go to Add. And then I could choose here the type of analysis that I want to do in my analysis case. We see here we have linear static, nonlinear static, construction stage analysis, consolidation. We have some coupled analysis, seepage. And we have here all the seismic ones, eigenvalue, response spectrum, time history linear, time history nonlinear, 2D equivalent, and some slope stabilities. So let's just say nonlinear static for very simple reasons. And here we see we have 2 windows. I have the window of everything I've created, the mesh sets. Default mesh set is where the building was imported into. And here are the boundary conditions that I just created and the loads that were imported. Let's just activate the dead load just quickly. And then I could just run the analysis. I have to save it. And then we could just run the analysis. Here we have a little icon of a guy running, solve, perform. And here I'll activate whatever I was doing. So we can briefly just let that run, and I can open something else. In this case, I've deactivated the building from the view. It's not deactivated in the analysis, but just for the view's sake, we see here some, in this case it's the displacements, the vertical displacements. I've done a cutting diagram. This is what the ground would look like, but I can make some cutting diagrams that allow me to see more directly what I'm interested in. And we can see directly here some results. I could probe some of these results of areas of interest directly on the surface. And then I can compare. In this case, I've done a comparison against another model where I had piles added to the structure. And if I wanted to see just directly there, this new distribution of results, what would be a structure with and without piles. We see here a different distribution. Sorry, I thought I was selecting the nodes directly there, but I think I just added some on the surface. We see here the different distribution of the displacements with the piles included in the model. So it's very easy just to make some of these analysis cases. Here we see that I have two analysis cases, the only difference being that in this other one, as I will open and show you, we can add the piles to be included, to be considered in the analysis, and then we run them in parallel and compare. And so that's one method of doing multiple analysis cases on the software, and then just being able to see directly, what would be your settlement, what would be your shear force on the slab. And so here we're seeing that same thing with the structure activated just for visual purposes, with the piles activated themselves. And then from there you could compare a settlement versus one pile versus the other. You can compare different size of piles or different distributions of the foundations, different cases for each, and then you can compare your results. So in a way you can model or design your foundation around that kind of analysis. So now finally we get to the part where we're going to do the same thing but for a bridge, import it from our Midas civil. In this case, I'm going to import an arch bridge, and I'm going to create this soil and abutment and the pile foundation around it, and then run the analysis, a time history analysis. Oh, sorry. So in this case, the only step I've done here was I imported the same kind of MXT file. Usually when it's imported, it's going to be just like this, where it doesn't show the properties being activated. The properties have been imported, as you can see here in the works tree. It looks yellow. It looks just like wires, but you can actually visualize these properties and activate them, just to for you to confirm that these have indeed been imported. And the other thing is also to save time, I've already defined the material properties as we had shown in the previous. So in this case, we have several ground layers. We have rock, we have some weathering soil, we have some soft rock that have been created for this analysis. But from here, we can go ahead and just start with the geometry aspect. In the other model, we've shown how to draw and extrude. In this case, we actually have a particular tutorial that's for a bridge abutment. So it shows all the steps for how to create the abutment itself, and gladly I will show you where you can find this video in this tutorial. But for this instance, again, for saving time, I'm just going to import this CAD file of that other model that has the ground created around it. So here it's just, we see there's different formats for CAD files that we can import. In this case, I'm importing a .xt format. And this basically is importing geometry, solids, lines, and surfaces. So what I'll do from here is I'm going to modify this geometry so that I can use it for my bridge. The first thing I want to do is I want to translate it. I go here to my Transform Translate tab. And I'm just going to select everything on the geometry aspect. And I could do it by direction. I could tell it, go X distance, and go y, then a different distance. Or I can use this function that's really neat that's called two-point vector. So all I have to do is tell it I want to connect this point from this structure with, let's say, this point of this other structure, and it'll calculate it for me after I press this distance button. And I also have a preview button here. So we see here in orange that it lights up, and it connects, it lights up exactly where I want it to. So I can just go ahead and do OK. So that's the first step. Now we can see here that the bridge itself is wider than the abutment that was created, in a different tutorial. It wasn't necessarily for this bridge in mind. It was just an example. But what I can do is I can modify the scale of my geometry to match this bridge. So I can go here again to transform scale, and I can again select my geometries. And what I want to do is first I want to tell it I want to keep it at a center, this being the position of where I want it relatively to be. But what I can do now is give it a non-uniform scaling. And what I'm really interested in this case is I want to make it wider. As we can see here, it's in the y-axis that I'm concerned with. So let's say I just say 1.5 scale factor. And if I go preview, it shows me, I can see in the blue where the original is, and it shows me in orange where it's going to be. But it also kind of lets me see that now the abutment will be wide enough for this bridge. So I can just go and say OK. And it does kind of look like that's, a good fit. So now what I can do is I can copy this geometry, mirror it around some planes so that I can then, I'm going to activate these planes in the origin, the XYZ origin of the model. I'm going to go here to mirror. Again, I'm going to select my geometries. And I'm going to select this plane just to keep it easy. And if I go to preview, I want to make a copy of it. And now I have my two geometries. And then again, I just have to translate this geometry. Again, using two-point vector to line it up. So I want this point to line up with this point. I go here to calculate the distance. And if I do preview, again, we see the structure now is going to line up nicely with where I want it. And we can see even the piles are being copied. This import was not just surfaces and solids, but I also imported geometries like lines and piles that were drawn in the other tutorial. So I can just go to OK. So now we have a pretty good setup of where we are. And so what I'm going to do is I'm going to actually merge some of these ground solids. As we see here, they're overlapping with each other. For that, we have Boolean operations. I'm going to use the command fuse. So I want to combine this with that, these first layers, go to apply. I want to combine the middle layer with the other middle layer, go to apply, and the bottom layer with the other bottom layer, and go to OK. So now if I deactivate from here my surfaces and my curves, we see that these are indeed now considered single solids. So in this point, I would be ready to mesh my geometries. What I'm going to do is to make sure that there's no problem with connections between these layers or these other geometries, I can check what we call duplicates. Basically, what Midas is considering a duplicate is something that was in touch with a different surface, and it has to light up orange for you to know that the meshing will be done properly. So in this case, we see we have different layers, soil layers. Since we have 3, we should expect to see 2 surfaces in between. And we also see that the abutments themselves light up, and that's just basically confirming to me that the abutment and the embankment are going to be properly connected. Had this not been the case, I couldn't use a tool called AutoConnect under the format or the method Boolean, and I could select, if I wanted to really just to be safe, I could just select everything and apply it, and then again do my AutoConnect. But in this case, we're fine. So now we're ready to mesh. What I'm going to do is first mesh the abutments so that I can properly connect the nodes of the bridge to the structure itself. So I'm going to first just hide this abutment, this embankment, and this embankment. You easily saw that all I had to do was, as I select something in my window, it lights up in my works tree, and I can easily choose it. So let's go to now the mesh window or tab. Everything we've been working on at this point, because it was geometry, was in the geometry tab. Now we can go to the mesh tab since we're ready to do meshing. So the program is very intuitive, very easy to follow in that respect. That once you're done with the meshing, then you move on to the type of analysis you want to do. You create the analysis case, and then you just see the results, right? So let's do some 3D meshing. I'm going to select this aboutment and this aboutment. I'm going to give it a size of 0.5. I'm going to give it the material property of the aboutment. And also, actually, because I have a structure in place that I want to make sure the nodes are going to merge, I can actually go here and expand this to some advanced options. We see here we have, amongst some things, you can create higher order elements and such, but we also see we have a tolerance for merging the nodes. So I'm going to reduce this tolerance so that I can guarantee that my nodes are properly connected. And then I'm going to deactivate the properties here to make it a little easier to see once we're merging. So here again, I can do the preview button, and if I close up, we see where the nodes are going to be, and we start to see that these nodes line up with the nodes of my structure. I mean, this was obviously predetermined, but you kind of have a sense of that if you know the dimensions of your structure or dimensions of both of your structures, you can give it a size or a size control that will allow these nodes to line up, and that way your tolerance makes sense. So then I can just apply this. And we see we run both, and now when I inspect it, we do see in fact that these nodes are connected. I can activate the nodes, and if I wanted to double check, I could just inspect the number. We see here there's no number overlapping. 31 node is shared by the bridge and the aboutment. We could actually apply different conditions for maybe releasing the moment or some other kind of like control on that connection, but for this case, let's just say it's it's merged, it's a rigid connection. So now I would I would mesh the rest of the structure. I'm going to mesh the aboutment mats or rafts. It has the same material property. Let's give it a bigger size. And again, I could inspect this connection, and we can see here that the nodes also lighten up nicely between the two sets, but because I give it a bigger size, it gradually grows away. So the software will do its best to connect the two different sizes, but then keep the rest a uniform size as you gave it. So then I can reactivate my embankments. I believe it's one of these. That's one, and this is the other. Okay. And I will mesh these embankments as well. All I have to do now is assign it a different property, embankment, give it a different name so it's easy to find. And then let's give it a bigger size just to keep it easier, and the file's not so heavy. So again, we see here we've meshed that, and again the connection is very small here, but it gradually grows. We can then mesh the first soil layer. In this case, we're going to say it's weathering soil. Let's give it an even different size. We mesh the middle layer, which would be the soft rock. And then we mesh the bottom layer, in this case, which would be just rock. Let's give it a bigger size. So we've essentially meshed all our solids, and now because we have some piles in this case, I'm going to deactivate everything and just leave the piles activated, or activate the geometry of the piles so we can mesh those as well. If I go here to my workstream, we see that there's a lot of lines that were imported from the other model, from the CAD file. But we see here that the parts correspond to the piles. It's actually separated by part and line. So I'm just going to deactivate the lines here, and that should leave me just my piles as we see now. So now I can just go to Mesh 1D. I'm going to select everything, assign it the pile property that I had already created. And then what I want to do is to properly simulate the interaction between the ground and the piles. Midas allows you to create or use interface. We have a particular interface for piles in which you can then just define some material properties. Let me show you here. this interface pile property, you would define some material, ground properties. Shear stiffness modulus KT has to do with what's tangent, and normal stiffness modulus has to do with what's normal to the surface of these, basically springs, of these piles. So we add those. Let's just separate these into interface. And then we can also simulate a pile tip. And again, for the pile tip, you can assign some properties like tip bearing capacity, tip spring stiffness to properly, I guess, model that behavior of the pile up against the ground. So for this, I just try to select only the nodes, the very last nodes. Of my piles. And so now I have the piles with the interface and the pile tips. What I want to do is actually, maybe it's just a custom from where we work. I'm going to add a constraint. I'm going to keep it from rotating in the C direction, the piles. So I can just activate this and call this RC. So now everything is meshed, and we would be ready to run a, depending on the boundary conditions and what we wanted to do, we're ready to run an analysis. So in this case, I'm going to first, because we're doing a seismic analysis, first we have to do a eigenvalue analysis. What I need to do is obtain the vibration modes of the two biggest modes with the most mass participation. So then we're going to use those periods, those frequencies of those vibration modes later for the damping method. So what I need to do here is first apply some ground surface springs. Let me go back to the presentation so you kind of see what I'm talking about or where we are. So we've done up to this part. We've meshed the ground and we've meshed the piles and everything. So I want to create these ground surface springs. Software will do this auto-calculated, automatically create this. But the only value I need to input is the modulus of elasticity coefficient. These are the equations used, and these are the terms that are used to auto-calculate this. The only, I just choose from this table, I'm going to choose the value 2. There's different tests and different methods to show how to get these values. There's a little more theory to it. But, for this purpose, time purpose, I'm just going to, take it from that table. Sorry, I believe, not this one here, okay. So I will go to Mesh, Elements, Create, Other, and from here we have, point springs, matrix, rigid links, elastin links. What I want to use is ground surface spring. And here is what I was showing. We input the modulus of coefficient, of elasticity coefficient, and it'll calculate for us the modulus of subgroup reaction. I also want to activate fixed bottom to simulate like a bedrock in this case. And from here on, I just have to select the sets of the solids. There should be 9 that I select in the end. And the program will calculate these surface spring properties depending on the material of the ground itself, or the properties of the ground itself for me. So from then, I can just create an eigenvalue analysis case and run this and get my vibration modes. We see here now, we see these little S's that are representing the surface springs, and we see the fixed boundary condition at the bottom. So now that I have these two, these boundary conditions, I can go here now to add what would be a eigenvalue analysis. And I activate the conditions and what I want to consider. In analysis control, I can tell it how many modes of vibration I wanted to consider. Let's say it's 30, and I can control some other things, define a water level, Sturm sequence check, mass calculate, or a couple mass calculations, stuff like that. And then I could just run it. And while this is running, let's just skip to a part that I've already done for time's sake. So here we see in the results, now we're in the post-processor. I have the vibration modes, and I also have this table. This table allows me, some information. We see here the periods and the cycles for all the different vibration modes. If I go to the bottom, I can see the percentage of mass participation. So in this case, we have case 1 and case 5, or mode 5, in the y direction. It says x, y. In the y direction, which is where the direction I want to apply my load, these seem to be the ones with the most participation. So I can go back and write down or copy what would be the, let's just say the period. We could also do it by frequency, but the periods of these modes. So in this case we have 0.952 and we have 0.637. So these numbers we're going to use later as a control of the damping for those principal modes of participation. So once we have that information, let me just pretend that I took a screenshot of that or I wrote it down somewhere. I will go back to my preprocessor mode, and what I want to do is add some dampers now to my boundary conditions. So I go back to Mesh, I go to Create, again I go to Other, and again I select Ground Surface Spring. This time I choose here Damping. I don't need to create another case for the fixed bottom. I'm just going to call these the dampers. And again I select the same soil layers, or basically all the solid layers, and I go to OK. Again, the program will calculate this for me automatically. We've seen here some of the vibration modes. We created this analysis case. This is what I was talking about, where we see the main modes with mass participation and we write down those periods. And then this is how the program automatically calculates for you the damping constant. And we have the primaries, the CP, the CS, the primary secondary waves. And we could also then now add, after adding these dampers, basically add the function for the ground acceleration. So what we will do is go back. We saw here, this was the original model that I left running. It took a minute to run the eigenvalue analysis for this model. Actually, I think I was in a different step where I've already added the ground springs, the dampers. Yes, this is the model that I was working with. So now I would go here to dynamic analysis, and what I would do is I would do here ground acceleration. I can choose the direction that I want to add it. We see here that we have a scale factor, so I could potentially add the same acceleration function in two directions. There's a different session, a different tutorial that we show where varying these scale factors, you can actually make it to be at an angle between the two. So what I want to do is here add a time function. I could choose one from our database. We have like earthquakes from all over the world, or you could actually just copy paste your own table from an Excel sheet. Let's say here I have different seismic, different time accelerations or acceleration functions for different earthquakes. I can just copy paste directly, Control V on my keyboard, and we have the acceleration function. Sorry, I had done this session earlier today and we're showing some different ones that I've applied. So from here then I just choose, this is off as reference to the name of the seismic, from the seismic function of Japan. And so I just create it. Let's just say 2. Okay. In this case, again, I'm sorry, I had done this session previously today and I forgot to undo what I had done. So here's just basically that ground acceleration we've created. We have the dampers. And so now we can just go and create a new analysis case for time history, nonlinear time history. And we would deactivate the ground surface springs. Midas allows you, if you have loads, you can convert those loads to masses to be considered for the seismic analysis. What we also want to consider are the dampers we created. Oh, in this case, they're already there. And the boundary conditions. So again, we do the fixed bottom, the rotation of the piles, and the dynamic function we did. Lastly, we do a time step. We want the time step here to match. We give it a length. We want it to match this increment period, to match the increment that we've been using or that we see in our time steps for the function itself. So in this case, it's 0.062. And we can vary the size of the output file by saying like every 10 steps give me a result. So here we see there's 162 steps. And lastly, what I need to do is I'm going to create here by the damping method input for the two principal, calculate the modal damping by the periods of what was the most participation that we got from our eigenvalue analysis. So if I recall, it was something like 9.35. You want to use all the digits that you can from your table, and we use a 5% damping. And then the second mode was something like 6.347 or something. And again, a 5%. Again, you probably use all the values from your table that you copied or you wrote down. And then from here, you just basically run the analysis, the time history analysis. For time purposes, let's just jump into one that I've already concluded. Here we have, I'm in the post processor, and I'm looking here at some of the results. We have all the different time steps. We can see here results for displacements of the ground. Again, I have a little tab down here. It can allow me to make a movie with all the different time steps of this earthquake. Here it's a little fast, but now it's actually going a little slower. I can save this format that I can then use in a presentation or such. We can also see results for reactions. We can see the accelerations, but also see structural results like your pile forces or your beam actual forces on your bridge or the bending moments and such. Lastly, what I want to show you is Midas recently added where you can do construction stage analysis and the last step be a seismic step, a time history analysis. So let's just say here we have the initial ground condition. This part itself has a material property of the ground. As I move down in my construction stages, we see here there's a step where this has been excavated, where the raft will go. And then in the next step, the structure itself has been installed with the piles, but the same mesh that has been reactivated with a different material property of the abutment. Then we have the embankment created around it. Then we have the bridge. And lastly, we will have like the other steps of the seismic function. So we can actually also do construction stage, keep those stresses from the construction stages, and then run a time history analysis. So I'm right at the time of the hour allotted. Basically, these are the steps that we just shown, the results, the bending moments. We can easily do by points. And so in conclusion, thanks to these advancements in what is numerical analysis, we've seen now the rapid rise of these superstructures, particularly in places that we probably wouldn't have seen before, the difficult ground conditions. And so we're seeing a lot of this development, let's say in the Middle East, where we have superstructures in soft or sandy grounds. It's all due to these new kinds of numerical analysis that allows us users to really get a good idea of how their raft and piles are going to behave with the ground through the direct method. Some more complicated ground conditions, which is the most important part of your project, you probably want to use the geotech software and ideally use the direct method.